This is lecture 3F for Calculus 1 on hyperbolic functions. There is an extensive analogy between the hyperbolic functions and the trig functions. You don't really understand, or you don't really get to see that correspondence until you start working with the complex numbers. But for right now, you can think of the hyperbolic functions as associated with a hyperbola. In a similar way, the trig functions were associated with a unit circle. But while we use the unit circle a lot with trig functions, we really don't use the hyperbola as much with hyperbolic functions. It's sort of an abstraction, and they're just treated that way. So like I say, in this class, the hyperbolic functions seem to be related to the trig functions in name only, but there really is a much deeper relationship between them. Here's how we abbreviate their names. The hyperbolic sine function is sinh, or S-I-N-H. The hyperbolic cosine function is cosh, or C-O-S-H. And then the hyperbolic tangent is T-A-N-H. So while you had sine, cosine, tangent, secant, cosecant, and cotangent for the trig functions, for the hyperbolics you have the same set. You've got hyperbolic sine, hyperbolic cosine, hyperbolic tangent, hyperbolic secant, hyperbolic cosecant, hyperbolic cotangent. And you use the same abbreviations like SIN, but after it for the hyperbolics you put the H. So you don't put the hyperbolic in front, you put it after the name. As we discussed before, some functions have long names. When we started to study functions, we gave them names with single letters, like, this is back in algebra, like f of x or g of x. And then there were some functions that had long names. Log has a long name, sine, cosine, tangent. Those are long names for functions. Hyperbolic sine here is a long name for a function. That means that the idea of function evaluation still applies. When I say f of x, and I write f parentheses x parentheses, that means that anything that's in that parentheses replaces the x in the formula. The x is the argument of the function. It's the same here. Hyperbolic sine, and in parentheses you see the x. That x is the argument of the hyperbolic sine, just as though it were a one-letter function. It does not mean that the x multiplies the hyperbolic sine. Like here, for example, if you took cosh and in parentheses said 5x plus 6, that does not mean that 5x plus 6 multiplies cosh, whatever it would be at that point. That is the argument of it. Once you evaluate that, then you would go to a calculator that had such formulas in it, or a different formula, and you would compute a value for the hyperbolic cosine based on that. Similar, it's the same way as log. Log is another long name, and what is after it is the argument of the log function. In the book you'll see some graphs of the hyperbolic functions, but for taking the derivatives we work with their definitions in terms of the exponential e. So hyperbolic sine is equal to e to the x minus e to the minus x over 2. Hyperbolic cosine is e to the x plus e to the minus x over 2. Then the definitions of all the other hyperbolic functions are, there's an analog with the trig functions. Hyperbolic sine is sine over, this should be an h there, cosh. Okay. Hyperbolic cosecant is 1 over the hyperbolic sine. Hyperbolic secant is 1 over the hyperbolic cosine. Cotangent, hyperbolic cotangent is 1 over the hyperbolic tangent. So all of those identities, those kind of definition identities, still hold. So you see a lot of that terminology coming forward. But here are these two basic definitions that we're going to work with. And this is how we're going to take the derivatives. Taking the derivatives of this hyperbolic functions is trivial. There's no big long proof like there was for that the derivative of sine x equals the cosine x. Here we just take the derivative of those exponentials. So if you take the derivative of e to the x, you just get e to the x. That's known. To take the derivative of e to the minus x, you need to use the chain rule. Okay. So I've worked it out here. I'm taking the derivative of e to the minus x. That will equal Well, the derivative of e to the minus x is e to the minus x. So I take the derivative of the exponential here, and then I have to take the derivative of negative x. The derivative of negative x is negative 1, which gives that a negative sign out in front. So the derivative of e to the x is e to the x. The derivative of e to the minus x is minus e to the minus x. And here's how we use them. So if I want to take the derivative of the hyperbolic sine, then I take the derivative of its definition. And by using the laws for taking the derivative, I can take any constant multiplier out in front, so I'll put the half in front. Then I just have to take the derivative of e to the x and subtract from it the derivative of e to the minus x. Well, the derivative of e to the x is just e to the x, so that goes right here. The derivative of e to the minus x is negative, but you already have a negative sign here, so those two make a positive, and we end up here with e to the x plus e to the minus x over 2, which is the expression for the hyperbolic cosine. Much easier to do this than it was for the sine, the trig functions. Okay, do the same thing for hyperbolic cosine. I want to take the derivative of hyperbolic cosine. So I take the derivative of its definition, which is e to the x plus e to the minus x. Since the derivative operator is linear, I can pull this 1/2 out in front and take the derivative of each term separately. So I take the derivative of e to the x, and I add to it the derivative of e to the minus x. The derivative of e to the x is e to the x, so I put that right there. Okay. Now, I take the derivative of e to the minus x, and that had a negative sign out in front, so that carries through here, and I get e to the x minus e to the minus x over 2, which is the hyperbolic sine of x. And notice that we had quite a few analogies between sines and cosines, and here we've seen sines, trig functions, and hyperbolic functions. And you see that here as well, but you notice there's a little sign difference. When I take the derivative of sine, I get cosine. When I take the derivative of cosine, I get negative sign. But with hyperbolics, that negative sign doesn't show up. Derivative of hyperbolic sine is hyperbolic cosine. The derivative of hyperbolic cosine is hyperbolic sine. So I've written that out so you can see it here. Here are the derivatives of those trig functions, and notice the negative sign. Here are the derivatives of the hyperbolic functions. They look very similar, but there is no negative sign. There's another analogy, and that is between this fundamental identity for the trig functions. We know that cosine squared plus sine squared is equal to 1. But when you get to the hyperbolics, you need a negative sign. So here we go. Cos squared minus sinh squared is equal to 1. So I have a negative sign here in this identity for hyperbolics where I had a plus sign for the trig functions. You can look in the book and see the graphs for the hyperbolic functions. They're very interesting, and there's some homework problems on just looking at the graphs and looking how they asymptotically start following the different exponentials. Hyperbolic cosine has an application to cables hanging between towers called a catenary. That will also be in a homework problem in the future. But for right now, what you need to know is how to take their derivatives. And here are the derivatives. Derivative of hyperbolic sine is a hyperbolic cosine. The derivative of hyperbolic cosine is sine, hyperbolic sine. And also helps to know the definitions of these functions. And here are their definitions. They're defined in terms of, where's the pencil? Okay. They're defined in terms of the exponent, e to the x. Hyperbolic sine is e to the x minus e to the minus x over 2. Hyperbolic cosine looks just about the same, but there's a plus sign, e to the x plus e to the minus x over 2.